Greetings! Welcome to Electronic Circuits 1. I am Behzad Razavi and this is lecture number 38. Today we will look at one more variant of the common source stage called the common source stage with degeneration, which has some nice properties and is used sometimes in circuit design. And then we will look at some other concepts related to biasing these types of stages. But before we go there, let's refresh our memory and see what we covered last time. We said that depending on the type of load that we connect from the drain of the amplifying device to VDD, to the power supply, we may have different types of common source stages. With a simple resistive load, if we include channel length modulation, the voltage gain is given by this. And we can replace the resistor with something else, maybe with a current source, because we are hoping to have a higher voltage gain, meaning that we're hoping this current source will have a higher impedance than this resistor. So we analyzed the current source, for example, a PMOS current source, and we saw that overall the voltage gain will be like this, and our hope is that RO2 is greater than RD. And many times that is possible. Okay, the circuit is also used very often in designing these amplifying stages. And finally, we saw another type of stage where the load consists of a diode-connected device. A diode-connected device is one whose gate and drain are shorted together. And we saw that from a small signal point of view, this device has an impedance of approximately 1 over GM. Or if we want to be more precise, 1 over GM in parallel with RO. So the overall voltage gain of the circuit will be given by minus GM of the amplifying device times the total resistance tied between the drain and AC ground. So we have 1 over GM2, we have RO2, and we have RO1, and that's how we get this expression. All right. Now before going to the last type of common source stage that we want to study here, we talked about one problem in circuit design, and that's what we call the problem of gain variation. We saw that when we analyze the gain of these stages, they are prone to change with the temperature, the process, meaning from one wafer to another wafer, with the supply voltage, and finally even with the signal level, meaning that if we apply a small signal here versus we apply a larger signal, the gain of the stage may vary. So the common source stage that we will look at now tries to address this variation and tries to reduce it. So let's see how that works. Okay, so today we'll start with the common source stage with degeneration. Then we apply this concept also just to current sources. They are not amplifiers, just current sources, but they can be degenerated. And it has some nice results from that. And then we will look at biasing techniques for this common source stage that we have studied. Very well. Let's begin with the degenerated common source stage. Degenerated CS stage. And the idea is quite simple. We take a common source stage as we have seen in the past, and we add a resistor from source to ground. Previously, the source was directly connected to ground. Now there's a resistor in between, RS. And like before, we have a resistor to VDD. This is our supply voltage, power supply. And then here we have, for example, a microphone. Again, I just use that as a simple generator of our input signal. And then we have a battery to make sure that this device is turned on and has enough overdrive voltage so that it carries a desired current. So that's what we call V0. Okay, the output, as usual, is taken from the drain with respect to ground, not with respect to the source. The common rail to us, the common reference, is the ground, not here. So this voltage is measured with respect to ground. Okay, so we would like to analyze the circuit. And if you remember, the analysis includes two steps. In the first step, we analyze the bias conditions. We have to find the VGS and VDS and make sure the device is in saturation. And then we have to find the bias current that flows through the device, because that bias current determines the GM and RO of the device, the small signal properties. So let's do that first. We start with step 1, bias conditions. When we are looking at bias conditions, we assume no signal is coming to the circuit. So this microphone generates 0. It's just a short circuit, if we model the microphone by an ideal voltage source. All right, so then what do we have? We have V0, the battery, connected between here and here, not between the gate and the source. So we need to write an equation, a KVL. This voltage is equal to V0, and that's equal to VGS of the device plus the drop across this resistor. The drop across this resistor is given by the resistor times the current flowing through it, and that is the drain current, drain and source current. So because the drain current flows through RS, I know how much voltage I have here. That's ID times RS. Therefore, the KVL gives me VGS is equal to, V0, this voltage is equal to this voltage, VGS, plus this voltage, ID times RS. In this equation, we have two unknowns, VGS and ID. V0 is known, is the battery we have connected, RS is known, everything, so it's just ID and VGS. Well, we have another relationship between ID and VGS. That is what the MOSFET itself imposes. So for the MOSFET, if it's in saturation, so I have to write here my assumption so that I don't forget. If it is in saturation, we don't know, but if it is, then ID has to be equal to 1/2 of mu n Cox W over L VGS minus VTH squared. And we don't worry about channel length modulation. In fact, for this entire problem, we assume that lambda is 0. Okay, so now it's not that hard. We have two equations and two unknowns, ID and VGS, and ID and VGS. For example, we can find ID from here, replace it here, and solve the quadratic equation. That allows us to find VGS and ID. Okay, so now that we have found ID, we're good, but we have to check one thing. We have to see if this device is in saturation or not. All right, so let's see what condition is necessary for that to happen. Well, we look at the gate voltage. The gate voltage with respect to ground is V0. Okay, so we need to look at the drain voltage and make sure that the drain voltage is not too low. By that we mean the drain voltage has to be greater than the gate voltage minus 1 threshold. All right? So the gate voltage minus 1 threshold is the minimum voltage that we can have at the drain. So let's see if that happens. So we're going to write the voltage at the drain. How much is that with respect to ground? Well, we have a battery of VDD from here to here. And then from that, we have to subtract the voltage across RD. That will give us the voltage from here to ground. The voltage across RD is, because ID flows through it, is ID times RD. So the drain voltage with respect to ground is equal to VDD minus ID times RD. For the device to be in saturation, therefore, so for saturation, this is what we need to happen. We need the drain voltage, VDD, minus ID times RD to be greater than or equal to the gate voltage minus 1 threshold. If the drain voltage is lower than this amount, if this voltage is less than this, then this device is in triode region. The drain is too low. The drain has to be higher. So if this condition holds, we are in saturation. If not, not. So when we are given the circuit with actual values and the parameters of the MOSFET, mu n Cox, VTH, W over L, then we proceed. First, we assume it is in saturation and calculate these things. And then we go and check this result. If this result doesn't hold, it means that this assumption is incorrect, right? This is for saturation. And now we could analyze the circuit again, but if in an amplifier like this, this device is in triode region, that amplifier is not very useful. So maybe we don't even need to analyze it. It's just a bad circuit design. We have to change it. Okay, so these steps, these belong to step number 1. They allow us to calculate VGS, ID, and then check to see if we are in saturation. Now we go to step number 2. In step number 2, we would like to analyze the small signal properties of the circuit, including the voltage gain and maybe the input and output impedances. So gain and input, output impedances. Okay, let's start with the gain. This circuit is not something we are familiar with, so we will have to draw the small signal model. No problem. Start from the left side. We replace the microphone with an AC voltage source, assuming that that's a good model for the microphone. V in. The battery is an independent source. It's a constant voltage source, so it goes to 0. So that goes to 0. Then we draw the small signal model of the transistor itself. So that's like this. V1 between gate and source. GM-V1 between drain and source. We don't have an RO because lambda is 0. Then from the source, we have a resistor to ground. So we have a resistor to ground. And then from the drain, we have a resistor to also ground because the supply voltage has 0 change with time. So it has to be a 0 volt supply, which means it's a short circuit to ground. So we have a resistor that also goes to AC ground, and that's what we have. We are interested in this output voltage with respect to ground. And what we would like to do is eliminate V1 so that we can find V out over V in. Okay, how do we go about doing that? Well, we can just make some observations before jumping into the equations. What we notice is that V out is from here to ground. So this is ground, right? Which means the current through RD is the voltage across it divided by RD. And that voltage is V out. So we say that this current flowing downward through RD is equal to V out over RD. That's great. Okay. All right. Now, here comes a little tricky part. Let me change the color of my pen. All right, so if the current going this way is V out over RD, what can I say about the current going this way? It has to be minus V out over RD because we have only this branch and no other branch. Because these two currents have to add up to 0, the current flowing to the left has to be minus V out over RD. Okay, so this current is minus V out over RD. Okay. All right, now this current happens to be equal to GMV1. So that's interesting. But there's also one other interesting point. This current flows through here, and flows through RS. It has nowhere else to go. So the current through RS happens to be this current, which is the same current as through RD, except with a negative sign. So RS and RD in this example carry the same small signal current, except for a negative sign. So if I assume the current through RD is V out over RD, not minus V out over RD, right? So we see that this current downward is also equal to minus V out over RD. All right. Okay. So now we have plenty of results to work with and to eliminate V1. The first thing that we observe is that GMV1 is equal to minus V out over RD. So that eliminates V1 right away. So we have GMV1 is equal to minus V out over RD, which means V1 is equal to minus V out over RD. Okay, that's good. All right, now that means that we have this voltage here. Let's go ahead and write a KVL around this loop. We say V in is equal to this voltage plus this voltage, right? So we say V in is equal to this voltage, which we have, minus V out over RD, plus this voltage, which is equal to the current through RS multiplied by RS. So the current through RS multiplied by RS. So minus V out over RD times RS. Okay, am I missing something here? Yes, so V1 is minus V out over GMRD. So this should be GMRD. Okay, so we're almost there. We are looking for V out over V in. So maybe I'll just try to write it here. V out over V in is equal to, as you can see, if I factor V minus V out here, I end up with 1 over GMRD plus RS over RD. I can factor RD out, so I end up with this expression. Minus RD over 1 over GM plus RS. This is the voltage gain of a common source stage with degeneration. Of course, if RS is 0, then we end up with minus GMRD, which we had before. Okay, that's an interesting result, and in fact, we often try to verbalize this result so that we remember it in the future, and we can easily apply it to more complex circuits. So we will write it like this. We say AV is equal to minus resistance tied between drain and AC ground. That's what this is, RD, the resistance that is tied between the drain and AC ground, this one. Okay, and the denominator, we have 1 over GM, we'll just keep it, plus the resistance tied between source and AC ground. So that's how we try to intuitively understand how this voltage gain expression is written. Okay, so once we have that, then if we have another more complex circuit and it can map into this topology, then we can readily write the voltage gain for it. Keep in mind that that expression and this expression are valid only for this case. Okay? Not for when lambda is not 0. Now, for some of the previous common source stages, we did include channel length modulation, if you remember. So what I showed you from last time here, remember that we had channel length modulation, all of these, right? So we could do that, except that in this stage with degeneration, it gets a little complex. In fact, I usually don't remember the expression for the stage if lambda is not 0. So we usually deal with that in more advanced courses. So in this course, we assume lambda is 0 for this degenerated stage if we want to find its voltage gain. Okay, so let's look at an example and see how we can use these results. So I have a little circuit here that I cooked up for you. Here's a diode connected load, call it M2. Here's an amplifying device, call it M1. I have some degeneration here, and I would like to find the voltage gain of this circuit, V in, V out. That's, of course, VDD. And again, we are assuming lambda is 0. Okay? I will give you 90 seconds to find the voltage gain of this circuit. Okay, so what do you have for the answers? Well, we just need to remember how to represent this diode-connected device as a load so that the circuit reduces to this circuit. And that's easy because if lambda equals 0, we know that the diode-connected device has an impedance of 1 over Gm. So this circuit reduces to something like this. So as the load, we have 1 over Gm2. This is a two-terminal device. And this is a two-terminal device, and that's modeled that. And then we have M1, Rs, and now we can write the voltage gain. So we go back there. It says the voltage gain is equal to minus the resistance tied between drain and AC ground. So that's 1 over Gm2 divided by 1 over Gm of the amplifying device, 1 over Gm1, plus the resistance tied between source and ground, so that's Rs. So that's the voltage gain of this particular circuit. Today in our series on Frontiers in Electronics, we will look at another application of circuit design and electronics in our lives. As you might know, electronics has found widespread application in monitoring the vital signs of patients. For example, the heart rate, blood pressure, and even brain activities. So today I'll show you an example of what we do to monitor the brain activity of patients. Here you can see, let's see if that works. We can see how we can measure the brain activity of a person. So every time a neuron in our brain fires, it generates a small electrical pulse that we can actually measure by placing a probe or an electrode on the skull of the patient. So for example, you can see these are probes or electrodes that measure the potential difference here. These are called action potential. And if you look at them as a function of time, we see that they do things like this. Every time a neuron fires, we get one of these impulses. And they have different sizes and shapes and so on. But these are the things that tell us how the person is thinking and how the person is feeling, etc. Okay, so today, this is a very nice way of understanding what the brain is doing. And we would like to have actually many of these electrodes, not just two. Because different parts of the brain produce different types of signals. And for that, we would need tens or even hundreds of these electrodes to be placed here. Now, the problem is that the impulse that we generate here is quite small. It might be a few millivolts. And we need to amplify this to a much larger level and then process it so that the doctor can actually capture these eventually and examine them and tries to understand them. So for that, what we do is something like this. It looks like a very complicated system, but let me take you through it. So here are the electrodes that are touching the brain and collecting the signals, those impulses that I showed you. So there's a bundle of them. In this example, there are 33 of them. These go to amplifiers. You see this low noise amplifier? So we have amplifiers here, lots of amplifiers. 31 amplifiers here. Okay, 32. This is LNA0, LNA31. We amplify them, then we go to something else. This is called pulse width modulation. This is to process the data and eventually convert it to digital data. We would like to go from these analog waveforms to some digital representation that's easier to process, store, transmit, etc. So then that goes through here and it reaches an oscillator, a voltage-controlled oscillator. Now this should be familiar. Remember in the Bluetooth example, we wanted to transmit data. What we did was apply the data to the control of an oscillator so that its frequency is modulated. And that's exactly what we do here. We modulate the frequency of this oscillator. The oscillator drives a power amplifier to deliver more power to the antenna. And this information is transmitted wirelessly. Why wirelessly? Well, because the patient wants to move around. You don't want to have so many wires hanging from the patient while the patient is moving around. So for that tetherless application, it's very nice to have a wireless connection between the patient and the monitoring system. So this information is transmitted out of the antenna, and it comes back, is received by the antenna. This antenna has some processing. You see FSK is similar to frequency modulation. So we receive that, process it, etc. And eventually we bring it back and show it here or show it on the laptop and so on. And the hope is that all of the circuitry here in this big box can be on a little device that we can attach to the brain. That device has to consume very little power so that this chip doesn't heat up. If it heats up, it's going to burn the tissue on the patient's brain. So that's one problem. Of course, the battery will run out quickly. So the challenge here is to design all of this for very low power consumption. And that's an interesting application of electronics. There's a great deal of research going on today on these types of circuits. Very well. We are now ready to apply the concept of degeneration to current sources as well. But before we go there, let's take a look at what exactly we gained from degeneration. We found the voltage gain of the circuit, and from that we can decide whether it addresses the issues that I mentioned before. We had the problem of gain variation with those parameters. have we resolved or alleviated that problem? Okay, so what we see here is that the voltage gain of the common source stage with degeneration is equal to minus RD over 1 over GM plus RS. Well, this says that if GM varies due to temperature, process, supply voltage, or signal level, the effect of GM variation is felt less in the circuit because of RS. You can imagine that if RS is very large compared to 1 over GM, so 1 over GM is negligible, then we don't even have dependence on GM, which means we don't have dependence on, for example, supply voltage or all these things. In fact, if we manage to do this, it's actually difficult in design, but if we manage to create this condition, so if we have this condition, 1 over GM is much less than RS. That means that, for example, we chose GM to be quite large, so that 1 over GM quite small. Then we have AV approximately equal to minus RD over RS. This is a beautiful relation because the voltage gain is the ratio of two resistors. And when you have two resistors built on the same wafer, the ratio is very well defined because it's just given by the geometries of the two devices. Even from one wafer to another wafer, the ratio of the two resistors changes very little. Similarly with temperature or anything else. So in this situation, if we manage to do that, the voltage gain is relatively independent of temperature, process, supply voltage, and signal level. Right? That's the extreme case. But in any case, even if 1 over GM is not negligible with respect to RS, its variations are swamped by RS. And that's why degeneration helps with those parameters that I mentioned before that change the gain of the circuit. So that's why we like degeneration. Sometimes we use it. We try to create this condition, but it's hard because either the GM of the device has to be very large, which is not that easy, or RS has to be very large, which also reduces the gain. You can see that if RS is very large, the gain is small. So we have limitations in terms of how far we can approach, how much we can approach this condition. Okay, so that's good. We saw that we have less dependence, but also the trade-off is that, as you can see here, previously the gain was just GM times RD. But now that I have degeneration, the gain is less, is RD over 1 over GM plus RS. So the price that we pay in making the circuit less sensitive to those variations is a reduced gain. That's a fact of life. That's the trade-off that the engineer has to make when he or she is designing the circuit. The gain will be lower, but the circuit will be less sensitive to process and temperature and supply and everything else. All right, so let's look at another concept here. Now, I said that the gain is smaller, and that's what comes out of the math. Is there any intuition behind this? Why is the gain of the circuit smaller when we have degeneration here? So let's just try to explore that. So why is the gain less with degeneration? All right. Okay, so I will draw the circuit in two versions, without degeneration and with, and then we'll play with them. So here's the circuit without degeneration. Here's the circuit with degeneration. And what we see is that the gain of the circuit is less than the gain of the circuit. Now, qualitatively, this is what we're going to do. Let's apply a change, a small change, to the gate voltage of this device here. Pretend that's the microphone signal, right? So we have proper bias. I'm not showing the bias. And then on top of the bias, we just have a small change coming from the microphone. All right, so we apply change here, and we apply the same change here. And now we would like to examine the effect caused by this change. Well, in the circuit on the left, when the gate goes up by delta V, VGS goes up by delta V. That's obvious, right? Because the source is grounded. So we see that VGS changes to VGS plus delta V. Okay, so then how much change do we have in this current from the bias value? GM times delta V, right? So we see that that means that ID goes to ID plus GM delta V. So far, so good. Now, let's look at the circuit here. The gate voltage goes up by delta V. What happens to the source voltage? The source voltage is no longer anchored to ground, so it could be constant, or it could go up, or it could go down. We don't know. All right, so let's assume the source voltage is constant and proceed and see what happens. If the final conclusion contradicts this assumption, obviously the assumption is wrong. All right, so let's see. And let's assume that this voltage is constant. The source voltage is constant even though the gate voltage goes up by delta V. Okay, if this voltage is constant, what can I say about this current? It's constant. So this current is constant. We put a question mark here because we're just playing right now. Okay, so if this current is constant and the source voltage is constant, then when the gate goes up by delta V, VGS goes up by delta V, right? The source is fixed. The gate goes up by delta V, so VGS goes up by delta V. But if VGS goes up by delta V, shouldn't the current through the device increase? Yes. Then this current cannot be constant. So right there, we have a contradiction. So then what could happen? Well, our intuition says that if the gate voltage goes up, the source voltage also has to go up to some extent. That's the only way. Because what we're thinking is, when the gate voltage goes up, the current of the device probably increases. And if this current increases, this voltage drop has to increase. So, if the gate voltage goes up, the source voltage has to go up to some extent. Maybe not as much as the gate, but to some extent. So we have some voltage change at the source node. All right, so here comes the interesting point. In this circuit, what we see is the gate voltage goes up. The source voltage goes up by some amount. That means that VGS does not increase by delta V. Right? Here, VGS increased by exactly delta V because the source was fixed, the gate went up by delta V. But here, it did not. The gate went up by delta V, the source did not go up by delta V. The source was not constant, the source went up by some amount. So this VGS changes by less than delta V because the source keeps going up. Whereas here, VGS changes by delta V. That means that the change in the drain current here is less than GM times delta V because VGS changes by less than delta V. Whereas here, the change in the drain current is GM times delta V. That tells us right away that this resistor has weakened this transistor. This transistor here used to be strong. It had some GM. From that GM, it would convert a change in voltage to a change in current, right, according to this equation. But this resistor has weakened it, so when we give it a change of delta V, it doesn't give us GM delta V. It gives us less than that. Okay? So that's why this circuit has less gain than this. The resistor has weakened this device. It's also linearized the device, and as a result, the gain has dropped. Okay, this is just for curiosity, for intuition, to see what happens. All right. Okay, so the next point of concern to us is the following. I just wanted to summarize some of the things that we have learned in the past. Okay, so let's talk about impedance of ideal voltage and current sources. We have encountered these in the past, but I have never formally explained these, so let's just go over this once so that you know exactly what this means. All right, so an ideal voltage source. I should say ideal and constant, okay? These are constant. Okay, so you buy a constant voltage source, a battery, and you are asked to find the impedance of this device. What do? Well, remember what we do. We place this in a black box, and we set all independent sources to 0. So this has to be set to 0. When the voltage source is set to 0, it becomes a short circuit. So this becomes a short circuit. And now we need to find the impedance between these 2 points. So for example, we try to do something like this, which is of course difficult because we're trying to apply some finite voltage across a short circuit. That doesn't really work. But anyway, this tells us that the impedance looking between these two is 0, right? Because for any finite voltage here, I get infinite current. So that means that the impedance, or the small signal impedance of an ideal constant voltage source is a short circuit, is 0. All right? So we say R equivalent is 0 for an ideal constant voltage source. Okay, how about the current source? So you buy a current source, well, we can't really buy current sources, but let's say you have a constant current source, and we would like to find its impedance. So as usual, we set all independent sources to 0. When a constant current source is set to 0, it becomes an open circuit. So here's what we have, an open circuit, and then we come along and, we come along and apply our Vx, try to measure Ix. Ix is 0, so that means that the equivalent impedance is infinity. It makes sense. It's an open circuit. An open circuit has an impedance of infinity. I just wanted you to have these in your notes so that from now on, anytime we encounter a constant voltage source or a constant current source, we can readily replace it by its equivalent impedance in small signal analysis. Okay, so in the next step, let's do something interesting. So let's build a current source. Now we've done that a number of times in the past, and we'll continue to do that because I'm hoping to improve the current source. Well, we remember that a MOSFET in saturation can approximate a current source. So here's our MOSFET in saturation, and this approximates a current source. You have some sort of bias voltage here. That gives a certain amount of current. So we said this is approximately equivalent to a current source with this side connected to ground. We saw that this is not an ideal current source if lambda is not 0, right? So if lambda is not 0, we see that this is no longer ideal, so not ideal. Why? Because what we remembered was that if we try to measure this current while we change this voltage, so ID versus, let me call this something else. So let's call this, for example, V1 and I1. Okay? Because we don't want to confuse ourselves with respect to the drain current and drain voltage. So we'll call this V1 and I1. So what we notice is that in this test, as we change this voltage, even in saturation, and we go up, the current is not quite constant because of channel length modulation. So the current goes up to some amount. Maybe I exaggerate a little, but that's what it looks like. All right, an ideal current source would have to generate a constant current regardless of the voltage on it, so it would be flat. All right, now I will play a trick. I will take a current source like before, but degenerate it by a resistor. What I'm hoping is that this will be better than the previous circuit. I'm hoping that this is a better current source. By better, I mean it's closer to the ideal, which means this won't be like this, it will be flatter. It will have less variation. So that's my hope. We'll have to see if that's true. So again, if I apply a voltage source here, V1, and I vary it, I vary this voltage, let's say, from 1 volt to 2 volts, or 1 volt to 3 volts, and I plot this current as a function of V1, then I'm hoping that this will be more constant than the previous circuit. Okay, so this is an interesting point, and to understand whether this happens or not, what we have to do is measure the impedance of this device. This is a two-terminal device. I can measure its impedance, the small signal impedance. That tells me whether this circuit is better than this circuit or not. Why? Because we just saw that if you have an ideal current source, its impedance is infinity. So the higher the impedance of a circuit that pretends to be a current source, the better that current source is, the closer to ideal it is, and therefore the more constant its current will be. So rather than try to plot I1 as a function of V1 for a circuit like this, I can look at the small signal impedance between these two nodes and compare that with that of this circuit. If the small signal impedance between these two nodes is higher than that of this circuit, it means that this is a better current source than this one, which means its current is more constant as we change the voltage across it. So let's go ahead and do that. We will draw the small signal model. So small signal impedance. So we start out from the left. This is an ideal constant voltage source. It's independent. It's set to 0. So that's set to 0. We draw the small signal model of the transistor. So we have this. That's the source. Now, obviously, if I'm interested in channel length modulation, I do need to include RO here. Otherwise, this would be infinite impedance, this would be infinite impedance, doesn't make a lot of sense. And then we have RS. So as far as the circuit over here is concerned, these two wires will be these two wires. And we'd like to find the impedance between these two. We already found the impedance between these two. We know from our previous calculations last time that that is just equal to RO. Now we're hoping that this will be greater than RO of the transistor. Okay, so let's go ahead and perform our usual test. We apply Vx, a small signal voltage, and measure the resulting small signal current, and that will give us the output impedance, the impedance of this current source. All right, so we have to analyze the circuit. As usual, we would like to eliminate V1 and then find Vx over Ix. Okay, Ix starts from here. It comes to this node and splits. Some of it flows through RO, some of it that way. But these two currents come back together here and reunite. So the current through this wire has to be equal to the current through this wire. Right? The charge cannot disappear. If the charge carriers come into here, they eventually have to come out of this wire. So here we also have Ix. And Ix comes through this wire. It has nowhere else to go but Rs. So the current through Rs is equal to Ix. The voltage drop across Rs is equal to Ix times Rs. Okay, that's good. Now, can I predict what V1 is? We see that the voltage from here to ground is Ix times Rs. The voltage from ground to here is V1. So V1 is just minus Ix times Rs. So V1 is equal to minus Ix times Rs. And this GMV1 now is known. It's GM times this value. So we know that. All right, so this really is a KVL around this loop, right? One voltage and another voltage, and they have to all add up to 0. That's the KVL. Now let's write a KCL here. Ix comes in. We lose some of it. How much do we lose? We lose Gm times V1. So the current lost here is equal to Gm times V1. So minus Ix times Rs. As you can see, I resist the temptation to define new parameters, new currents, and new voltages. And I try to find everything that I can and just mark it on the circuit itself so that all the information is in front of me and I can utilize the different pieces to write the final equation. All right, so Ix comes in and we lose this much of it. The rest of that current has to flow through RO. So the current through RO is equal to Ix minus this current. So the current through RO is equal to Ix minus this current plus Gm Ix times Rs. So step by step. If this is difficult to digest, pause the recording and think about it for a minute. All right, so what we have so far is the current through RO is equal to Ix plus Gm Ix Rs. That readily gives us the voltage drop across RO. I just multiply this by RO, I get the voltage from here to here. All right, so what do I do with that voltage? Well, we write a KVL in the output network. This voltage is equal to this voltage plus this voltage, right? So Vx is equal to RO times the current through it plus this voltage, which is Ix times Rs. So if we write a KVL in the output network, we get Vx is equal to this voltage is equal to this voltage, RO times the current through it. So RO times Ix plus Gm Ix times Rs. And then this voltage, which is Ix times Rs, plus Ix times Rs. All right, so just one equation. And now we can find Vx over Ix, which is the impedance of this entire current source, as seen between these two nodes. So we see that Vx over Ix is equal to, we have 1 plus GmRs times RO, 1 plus GmRs times RO plus Rs. That's one way of writing it. You can also write it as 1 plus GmRO times Rs plus RO. And both of these are useful methods of writing this, so whichever you like. I generally go with the bottom one, but the top one is also useful in some cases. All right, so let's verbalize this result. This circuit this current source, with this degeneration, will accompany you through many courses in the future. This is a beautiful result, and you have to memorize this. This is very important. I don't use the word very, very often, but this is very important. Okay, so this says that as a result of degeneration, this RS, the output impedance of the current source, which used to be RO, has risen to this value. You can say RO has been boosted by 1 plus GMRS, and then we added another RS. Or we can say we have multiplied the RS in the source network by 1 plus the intrinsic gain of the device, and then we added RO. So whichever you like shows that the output impedance of this new circuit is higher than that of the old circuit as a result of degeneration. Okay, so that's what we get for the degenerated current source. And let me check here. So let me give you an example. I will build a current source like this, but I don't want to use a resistor here. I want to use something else. I want to use a current source, actually. I'm allowed to do that, right? This is a two-terminal device. I can use other two-terminal devices that can pass a DC current through them. This is a DC current source, right? So we can have a resistor, but we can also have a current source. How do we build a current source? Well, like this or like this, right? So let's do that. Let's take our transistor, call this M1, and we have a battery here, of course, to bias it up. But instead of a resistor, I want to have a current source. So how do I have a current source? Well, I can build a current source using another MOS device, right? Like so. Is that okay? So you see that this current source resembles the good old current source that we had here without degeneration. And now this whole current source is degenerating this device. This whole current source is acting as this RS here. And what we would like to do is find the impedance of this two-terminal device from here to here. Now you look at it and say, oh my God, I have two transistors. I have to draw the small signal model of this, small signal model of this, and solve it. You could do that, but you don't have to. Because what we do remember is that this little box here, which is this little box here, can be represented by one resistor equal to RO of the device, assuming that, of course, all of these are in saturation. So I can quickly draw the circuit like this. I can say this is RO2, representing this entire current source here. And then I still have the rest of the circuit, M1. Again, I'm mixing small signal and the schematics together. This is small signal, this is schematics, and so forth, bias conditions, all that. But don't worry about it, it's okay. So now this circuit maps to this circuit. The only things that we have called RS are O2. So the result that we obtained before is readily applicable. We just need to change RS to RO2, RO to RO1, and GM to GM1. Because GMRO belonged to the original current source transistor. So we say that R out, or R equivalent, I guess I called it R equivalent before, R equivalent is equal to this expression, or that, whichever you like. So 1 plus GM1 RO1 times RS. RS happens to be RO2 plus RO1. So that is the output impedance of this strange-looking structure. This strange-looking structure also will accompany you in many courses in the future because it has many applications. We call this a cascode structure. But for now, don't worry about it. It's just a simple example. All right. Our time is up. Next time, we will take these ideas and apply them further. I will see you next time.